Okay, I think more or less we have a good number of people to start, and those who are late will catch up later. So good morning again, and today we're going to close this overview of the adversarial machine learning field, and I'm going to discuss some other attacks against machine learning. And before that, we're gonna see some techniques that we can use to mitigate the threat of evasion attacks. So where you have an attacker that manipulates test data to mislead classification. And we will also see a demo that we have on a website, so you can also use it yourself. And that shows simple examples on how you can manipulate images to fool a simple classifier. Okay, so that will be part of this lecture. So about the defenses, there have been several proposed defenses that turned out to be not very effective against evasion attacks. I'm not going to cover all of the possible defenses that have been proposed because there are just too many. It will take us a couple of weeks, I think, to discuss all the methods in detail. So what I'm trying to give here is an overview of the main approaches or the main categories of approach that I think work the most against this threat. And to keep it very simple, we can categorize them into two main different approaches. One is essentially aimed to reduce the sensitivity of the classification function to input changes, because as we discussed yesterday, this is one of the main problems behind the vulnerability of classifiers against evasion attacks. And we will discuss more about this in detail in a minute. And this encompasses approaches named, so one is named adversarial training, which essentially amounts to retrain the classifier on some of these adversarial examples. So you create some perturbed images, you retrain the classifier on them, and then you see that the performance under attack improves a little bit, okay? And this is also equivalent, we'll see how, to a different regularization approach, okay? And I think this is very interesting, and we will discuss that soon. And the other bunch of defenses that one can use, which are complementary, by the way, to the previous approach, so you can use them together to strengthen your classifier, is based on the idea of rejecting samples. So the issue now with standard machine learning algorithms is that they have to make a decision anyway on every given point. So you give them a point, and even if it's not in the known classes, they have any way to assign it to one of these classes. With rejection, you give the classifier the option to abstain. So to say, I don't know, or I cannot classify reliably this sample, and so I just don't give I don't make any decision on this point. This is the idea. So regarding the first approach, the idea here is that you can learn a classifier by using what is called robust optimization, which means making the classifier aware that the data points can change. And so normally, this can be done by formulating this minimax problem, where now look for a moment to the standard learning problem, which would just have the minimizer here. So in the standard learning problem, you just minimize a loss function computed on the training set with respect to the classifier parameters. So that's the outer optimization loop. Okay, so this is the minimization of this loss function with respect to W. That's how you optimize the parameters of a linear classifier, okay? So what we do here, and this would be the solution that you find, for example, to separate these points in a very simple toy example. Now, what we do with the inner loop is that we assume that these data points can be perturbed by some delta, and this delta is constrained to be in some region of the space. So if you set a bound on the max norm of the perturbation, it means you are basically plotting hypercubes on each data point, and hypercube on each data point, and now the attacker can shift the point within this domain, okay, within the hypercube. And maximizing the loss function with respect to this kind of perturbation means that you shift the points towards the boundary in order to improve the chances of having such points misclassified. In practice, it means that this training point will change as shown in the picture. Okay, so that's what the inner optimization loop does. So it's essentially manipulating all the training points and creating adversarial examples out of them. Okay, and then what you do, this is an iterative process. So you train the classifier, you modify the samples, then you retrain the classifier, and so on and so forth, until you reach some equilibrium point. And then if you retrain the classifier, in this case, what you get is this, again, this classifier that separates now the perturbed version of the training points. Okay, so that's the basic idea behind formulating this learning problem as a robust optimization problem. Now, and so in its standard form, this amounts to what is called adversarial training. Essentially, it's the idea of retraining on the adversarial examples for different times and so on. Now, the interesting is that under some assumptions, you can show that this robust optimization problem is equivalent to a regularized problem, where the regularization term is basically dependent on the size of the gradient that you have on the training points. So what you're trying to do with this approach is penalizing the size, the gradient, the norm of the gradient on each training point, which means I want that my function is smoother on those points. Okay, so what you get is essentially you push the boundary farther away from the points in a given direction. Now, the interesting thing here is that this kind of regularization, so the norm of the gradient that you use here, matches in some sense the norm of the noise. And in particular, it is the dual norm. So if you assume that the noise is bounded by the max norm, which means you have squares here or hypercubes, then you have to penalize the L1 norm of the gradient. That will be the optimal regularizer against this kind of noise. And then if you use instead Euclidean noise, you have the Euclidean regularization, the Euclidean norm for regularization. And this is a very interesting finding, which clearly here only holds for linear classifiers. So this will basically be the weights that you have in your classifier. But I think it's really nice because it connects the kind of noise that you have with regularization. So if you prefer, you can think of regularization in a different way now. So these regularization terms do not come from bounds on the generalization error for learning algorithms, but here you're just saying, so there's no assumption on the underlying distribution here of generating the data samples. You are just given a bunch of data points on a vector space, and you want to find the separator. And now the regularization term essentially tells you that the separator is tuned based on the kind of noise that you assume on the data. So it's a different way of seeing what regularization does. Okay, so it's matching a specific kind of noise. And so this is one kind of way you can use to improve the robustness of classifiers against some adversarial examples. Okay. And we did some tests. If you recall, yesterday we've seen the case of Android malware, where we trained a linear classifier to discriminate between benign and malicious applications on Android. And if you think to the kind of attacks that we performed, so the idea was to inject objects into Android applications in a way that their classification goes from malicious to benign. And this attack can be seen as a sparse attack because the attacker injects one object at a time and aims to reduce the number of objects as much as possible. Okay, so in some sense, it's a sparse attack. And then the dual norm of the sparse attack, of the sparse noise, is the infinity norm. And therefore, according to this robust optimization approach, this classifier that penalizes the set of weights using the max norm should be the optimal response against a sparse noise, a sparse perturbation of your data points. And in fact, when you test it, so this is a plot that shows, again, the correctly detected malicious application where you have 1% of false alarms, so legitimate applications misclassified as malicious. So it's the detection rate. And if you recall, we've seen the green curve, and this is 95% more or less, so 95% of malware is correctly detected by just injecting 5 to 15 objects in each malware application, you can flip the decision, almost on overall samples. The blue line is an empirical defense based on combining different kinds of classifiers and averaging or doing majority voting, which is one thing. So that there is one claim, one intuitive claim is that if you have multiple classifiers, they are harder to fool than a single one. And it's not completely true. It depends on how you combine things. But in the end, it gives you some more robustness, because you see that their detection rate under attack decreases more gracefully than the other curve. And now if you look at the red curves, they are essentially variants of this classifier, which is assumed to be the optimal response in this case. And as you can see, the red curve is essentially, this classifier is much more robust than the other two. And to fool it, you have to change, to fool it with 100% probability, you have to change more than 100 objects. So you have to inject more than 100 objects into your Android application. And this may be feasible anyway, but it's much harder than changing less elements without corrupting the intrusive functionality of the code. Of course, in the end, you will fool every classifier anyway, because we are just looking at static features. So we are just looking at it's a static analysis from the code. So you can manipulate the code to preserve, let's say, the behavior of the program, but you can change it in many different ways. So that's not enough to identify malware. In these files, you should complement the analysis with some dynamic analysis, which means you execute the program and you see what it does, if it connects to some suspicious servers or these kind of things. But just looking at the static code, the static analysis of the code is not enough to perform malware analysis completely. Okay, that's just a very fast approach to identify trivial malware samples, let's say. If you want to really catch the difficult ones, you have also to perform some dynamic analysis. But that's a general problem of program analysis, okay? It's outside of this machine learning robustness thing. And now it is interesting also to explain why this approach is significantly better than the other one, than the standard classifier. And the reason is that, as I told you yesterday, the standard SVM, the standard classifier, tends to overemphasize few features, which means you will have few features that are given a very high absolute weight. And for example, this is depicted in green. So assume that if you sort the absolute weight values given to the features, you have something like the green case for the standard SVM. And therefore, it's clear that if the attacker changes the first two features, it can significantly change the output of the classifier, right? What happens when you penalize the max norm of the weights is that essentially you are bounding the weights to have the absolute value within a given small interval. And so it means that if you really push the regularizer, it happens that your classifier more or less learns the same weight in absolute value for all features. Of course, there will be positive and negative ones, but they are bounded to be very small. And so by changing a single feature, the attacker cannot have a significant impact on the classifier output. To have a significant impact on the classifier output, you need to change a lot of features. So you need to change much more. And that's why you have this kind of behavior in these security evaluation curves. So they tend to decrease in a much more gracefully manner. Okay, is that clear to everybody? So we have, in some sense, a theoretical guarantee that this is the optimal response, but there's also an intuitive explanation why it's more robust than the other classifier. And that's for the first defense. Of course, as I told you, this is also equivalent to adversarial training. It has been shown that for a small perturbation, penalizing the gradient on the training point, the input gradient of the training points is equivalent to retrain on these adversarial samples. And if you want to see it in terms of sensitivity, what happens is that you are decreasing the local sensitivity of the function around the training points. And that's why the classifier becomes more robust. Okay, of course, the important thing is that this notion of sensitivity has to be related to the kind of noise that you have. Okay, so you have to smooth the function in a proper way. It's not enough to smooth it according to any regularizer. About just a quick note about ineffective defenses now. why several defenses that have been proposed are not really effective against the attack. The reason is that they're not really changing the classifier. They're not really moving the boundary. So what they're doing is they're making the optimization of the attacks more complex. So if you have, so this is the case, right, where we've been analyzing so far, where you have a smooth function that you can, where you can optimize the attack points in a very easy way. So the function is smooth enough so you can perform easily gradient descent on that to optimize your points, your attack points. And so many defenses, more or less explicitly, perturb this function, the classification function, in this way. So now the classification function can be made very noisy. And of course, when you try to optimize the attack points, so if you start from X, for example, then you will end up in a very close local minimum. And so your attack algorithm will stop here, creating an adversarial example that is not evading detection. But this is not because the classifier is really more secure. It's just that optimizing the attack points is much harder in this case. And so to defeat these kind of defenses, you can simply smooth again this function, smooth out the function, for example, learning a similar classifier which has a smoother surface. And then it can be optimized again with gradient descent in an easy way. And so this is essentially what this paper has done. So what Nicolas Carlini and Anish Atali have done to break all these defenses from ICLR 2017. Okay, it's a very simple idea. So create a smoother function that you can again optimize very easily, and then in this way you can discover that there are many approaches which are not really effective to defend against this threat. Some other defenses, so this is one kind of defenses, and the other one was essentially learning almost a step function. So if you make your classifier non-differentiable, of course you cannot optimize the attack points by using gradient descent, because the gradient is 0 almost everywhere. So what you need to do is to create, again, a smooth approximation of the target function. So that's the overall idea, just in a nutshell, okay? And that's about the first line of, let's say, effective defenses against evasion. Now talking about the rejection, the reject option, we can see that it works in this way. So if you have two classes and you have a decision function, normally the classifier, as I said before, has to make a decision on every possible input. And therefore, it has to make a decision also for these green points, despite they are very far from the rest of the training data, right? So these may be images of cats, images of dogs, and this may be a completely noisy image, very far from the rest. But given the classification algorithms that we have nowadays, they have to make a decision anyway, even on that point. And so in this case, this point will be classified as a blue point, okay? With rejection, what you can do is try to shape the decision function in a way which is more tightly enclosing the classes, and therefore you can have the boundary which is closer to the red points and to the blue points, and outside of these regions, you just say, I don't know. So the classifier just doesn't make any decision. Okay? You can think of it as an additional class where you say, I don't know, or this is an anomaly, an anomalous samples, which I cannot make a reliable decision on. We tested that in the case of the ICAB robot. If you remember yesterday, I just described this thing. And this is just an example, again, of an adversarial example against this system. So you have a plate, you manipulate some of the pixels with more or less a noise, and then you have this image misclassified as a cup. This is the noise mask, and this is the cup from the other class. And now, what happens when we apply rejection in this case? So in this case, the green and the yellow curves are just the standard SVM classifiers trained on top of the deep net that extracts the features from the images. And here you have that more or less the accuracy is 70% here. Recall that we have 28 classes of objects, so it's not that bad. And this is what happens when you increase the amount of perturbation on the images. according to the L2 norm, so the Euclidean distance. Of course, as soon as you increase the level of noise, the performance drops, and you see that it drops quite quickly here. So this is about 200 in terms of the Euclidean distance with respect to the original image. So this is not a very strong perturbation, but it's enough to almost completely mislead the classification accuracy. Okay. The red curve is using the rejection option, again, only in the last layer, so at the output of the deep net, in the representation space. And so at the beginning, where you have no adversarial examples, it's clear that the accuracy decreases a bit, just because you are more tightly enclosing the classes, and therefore you will reject some legitimate samples. And that's something, the price you have to pay to gain some robustness in this case. And therefore, when you have a very small perturbation, it jumps over 80% just because it's able to detect most of the adversarial examples. So all samples are now adversarial examples, and you can catch correctly 80% of them. So in this case, it's rejecting pretty much everything because everything is an attack. So in this case, when you increase the perturbation, we manipulate all the test images. Okay? But then you see that there is, again, a decrease in the detection rate for the adversarial examples. And the reason is that we are just working on the representation space. And what happens in the representation space is that these samples are then projected very close to the target classes. So this is very well depicted here. So what happens is that you have the original image, and this is the perturbed image. And now they are very close in this pixel space, right, in the space of images. But what happens is that while the original image is projected in a given region of the representation space, the corresponding perturbed version is projected much closer to the target class. So if you want to have this car misclassified as a dog, the corresponding adversarial example image will be very close to the class of dogs in the representation space. And therefore, that's why you cannot reject correctly this sample in this space anymore. Because if it's too close to the other class, there's no way you can distinguish these samples from the others. Okay? So that's the best explanation I found why this is not effective. And so you need to basically apply rejection at the lower layers, not just at the last one. And this is another nice explanation that I found in another paper by David Evans and colleagues. And this depicts the distance between the input sample and the adversarial example across different layers of the networks. So you start from the input space, and then you go up to the last layer. Okay? The red line is an image perturbed with an attack algorithm, so it's an adversarial example. The blue one is just a random perturbation. So it's the distance between the original image and the randomly perturbed one, I think with Gaussian noise, or anyway, a noise which is not adversarial against the classifier. And what you see is that more or less this distance is constant up to some level, but then they go very far. So the adversarial sample goes very far with respect to the original image in the last layers. And then this is essentially another view of the same problem we discussed before. Okay? Whereas for the random noise, this distance gets smoothed, by the way. So as you increase the level of the layer, towards the output, then the image it gets correctly projected against, close to the original class. And so essentially, this noise doesn't get amplified, whereas the red noise, so the adversarial noise, gets amplified throughout the layers. So that's the main problem.
So I guess you're suggesting then that to counterattack this kind of attacks, it's better to work even at the pixel level. I mean, at the very initial layer. I mean, you can probably reject these adversarial examples without looking at the representation at level, but
more or less what I'm saying is that it's not enough to look what happens at this layer, because that's already too late. They are already indistinguishable from the target class. So what you should do is go back unless they become distinguishable again. Probably it's not required to go up to the input layer, but maybe, I mean, if you do that for 10 layers in this case, you may be able to get a lot of these adversarial examples. Of course, the problem is you may reject too many legitimate samples. So this is something that we should look into in more detail. Okay, but that's part of the story. Okay, now I have. I just want to show you a simple demo that we created with some students, some colleagues, Ambra De Montis and Marco Melis. And you can also connect to this website. So there's a simple demo where you can modify, you can select some input digits, so from the MNIST data set. You can select the target class, the amount of perturbation, and see what happens to the output of a multi-class linear SVM. Okay, I'm just showing you a simple example. Then if you're curious, you can try it yourself later. Okay, so that's the website. You can pick some digits here. Let's take 0, for example. And then you can select the target class. Now, if you remember yesterday, we've seen two different kinds of attack. One is the error generic one, where you do not specify any target class. So the only thing that is of interest to the attacker is having just an error. If the 0 is misclassified as a 1, a 2, or whatever, it's the same for the attacker. In the other case, instead, the attacker wants to specify also the target class. So you may say, I want this image of a 0 to be misclassified as a 6. Okay, so you specify the target. And here, you can either pick any or select one of the digits. Let's take 5, for example. I'm not sure if you can see it. Okay. And then here you can select the amount of perturbation, which is the one that it's the epsilon, essentially. Okay, it doesn't change. Okay, let's see what happens if we perturb 0 with a very large perturbation. I don't know why it was not changing that. It takes some time, so there are a couple of workstations that are doing the computation in our lab. So probably if you're using all the demo at the same time, you're going to wait for a while. But this is what happens. So first of all, you see that now the image of the 0 has been completely destroyed. So this is, for us, almost a completely random image, right? But this is, for the classifier, this is really a 5 with a very high confidence. Okay, so the classifier is very confident that this is an image of a 5. And you can see that, so these were the original scores. And as you can see at the beginning, the 0 was classified correctly, because 0 is the class which has the highest support, the highest confidence from the classifier. And after the perturbation, you see that the classifier believes it is a 5 with a very high score. Okay? And so this essentially tells us that this classifier is not learning any structure, any semantic meaning of the digits, right? This is not really a 0. Well, it resembles, I must say it resembles a 5 more or less, but it's anyway very noisy, okay, with a lot of fantasy. Okay, and then you can try different things. You can try with less noise, and then you gradually increase the level of noise, and you see that the perturbation increases, and gradually the digits tend to belong to the other class. It's interesting also to see that, for example, in some cases, here, for example, if you have 0, 1 is the class with the least support, right? So when you want to change this image of 0 to 1, and the perturbation is not sufficient, it may be misclassified as some other classes in between. So it might be misclassified as 5, 2, or 7, for example, okay? Because if you imagine that in the feature space, what happens is that you have the class of zeros, and then the class of 1 is very far from there. So, and you're shifting the point in this direction, essentially, and in the middle, there are different classes. So it's crossing different classes in the feature space up to reach 6 when the perturbation is sufficient. And you can test that by playing with this Dmax or epsilon parameter in the demo. Okay. So that was for the demo part. If there are no questions, I also like to point out another thing. So we are also with the company, we are, with Pluribus One, we are also involved in an European project, which is called ALOA. And here the goal is to essentially design, the goal of the project is to design deep networks, also taking into account architectural constraints that come from heterogeneous hardware. So the goal is to take deep nets and make them fit to these small devices, heterogeneous devices, in a way that you can then use them in video surveillance cameras or robots, you know, where you have this custom hardware. That's the goal of the project. And normally what happens is that you take a pre-trained deep net and you try to approximate it to make it possible to fit to the hardware requirements. And so instead of using representations of the weights, for example, in using a lot of bits in floating point, you reduce the number of bits to represent the weight, so introduce some approximations, and this typically degrades the performance. So the goal of the project is to put them, these requirements together, so you design the network already, keep into account also these constraints. And in this part, in this project, we are responsible for doing the security evaluation. So to run these attack algorithms and see in the different use cases how they perform. Okay, so that was just another curiosity that I wanted to tell you about evasion attacks. So if there are no questions, this essentially closes the part on evasion, which is the case of adversarial examples where we had most of the work done. And I'm now shifting to a different kind of attack, which is called poisoning. Okay? Yeah. Yes, please. Which one, sorry?
I mean, you said that you're working on the security aspect of this heterogeneous approach to neural networks. So what are the differences?
Oh, no. That was just, we're analyzing, so when you design the network together with the hardware constraints, you essentially use additional constraints, and then we want to see whether we are changing the security properties or the robustness properties of these networks when we introduce these approximations.
And basically, you successfully try not to change it. So you succeed
in
not changing them. It's not a problem. The heterogeneous environment is not a problem for the security.
We test that. So, and then of course there is the interest is to see whether these algorithms are can be fooled and to what extent. So the goal is always the same. So try to understand the level of robustness against this kind of worst-case noise. But then we see also what happens when you introduce these further design constraints. So when you try to shrink the network to make it fit to these embedded devices. If that compromises accuracy or robustness, and in which ways. So that's the role we have in that project. Okay. So I'm now moving on to poisoning. In the case of poisoning, we have a different problem. So now the attacker is not changing the test data. What it does is manipulating the training data. And here again, you can have different objectives. So just to sketch the problem a bit more in detail, normally you have your training data with labels, and then you train a classifier which works well on some unseen data, on the test data. And typically for spam, you have a collection of labeled spam and legitimate emails. You create a dictionary of words, and then you train your classifier on these. So in the poisoning setting, to explain the poisoning setting, you can think that there is an attacker now that sends you some spam messages, as before, but they also contain some good words. So words which typically appear in your legitimate emails. And maybe, as I said, this can also be colored in white, so that when you get the email, you just read the spam message. Then you are prone to classify this email as spam, and so you flag it as spam, and your filter is updated, right? So it is retrained, also including this sample in the training set. Now, when it happens, and if it happens several times, you may end up having a classifier that considers these words, university and campus, which were good words, they can be considered bad words by the classifier. And if this happens, several of your legitimate emails may end up in the spam folder. Okay, so the goal here is to find some training samples that maximize the error of the classifier on the clean data. Okay, and this would cause a denial of service for legitimate users. So that's the main goal of poisoning attacks. The attacker can change some training data in order to maximize the error that you have on clean data. And therefore, we can also formalize this according to the attack framework. So the goal is to maximize the error. We start by assuming, as usual, the white box setting, so the attacker knows everything, because we're just interested in understanding which is the worst case performance. And then we can relax this assumption to see what happens when the attacker knows less about your system. But first thing to do is the white box case. So I want to see my system, how much is robust against an attacker which is very powerful. And then in this setting, the attacker can inject some poisoning samples into the training set. And so the optimal strategy, now I state it in words, but then we will formalize that. But it is that the goal is to find an optimal attack point, XC. So let's simplify the problem a little bit. Instead of considering many points at a time, we just focus on a single poisoning point. So the attacker wants to find the poisoning point XC that maximizes the error of the classifier. Now, to exemplify this again a little bit more, assume that you have a linear classifier. It's a linear SVM in this case, and you have two classes. And now these are the training samples. So you train the classifier on these samples, you got this linear separator, and then you measure the error on a separate data set. Okay? Not on the points that are in the slide, but on a separate data set sampled from the same distribution. So in this case, the error is 2%. If you add a red point here, XC, what happens is that the boundary learns this point as well. So the classifier learns this point, and the boundary changes a little bit. And now if you measure the error, it raises to almost 4%. And the error, recall that it's always measured on the separate data set. Now the question is that I don't want to to throw random points into the training set, right? I just want to carefully find the XC, which is the one that maximizes the error on the clean data. So to see it in 2 dimensions, you can basically move XC in. You can create a poisoning point in each location of the space. So you can do this kind of exhaustive analysis in 2D because it's doable, but for larger dimensions, it's not possible. And for each location, you take the classifier and you retrain it by using the training data plus the current location, so the current XC. So for every point in that plot, you retrain the classifier once, including XC as a training point, and then you measure the error on the separate clean data set. And this is what is depicted in colors. So that's the classification error as a function of the training point, essentially. That's what we want to maximize. And as you can see, this function has this kind of behavior. If you add the red point in this region, nothing happens, essentially. And in fact, what happens for the SVM is that this point is just learned as a reserve vector. So it has absolutely no impact on the decision boundary. Okay? So that's why the function is flat here. The classification error is not changing because the classifier is not changing when you add XC in this region of the space to the left, in the left part of the plot. Whereas when you start adding the point here, you see that the maximum is more or less here in the lower right corner. And in fact, this is where you get more or less 5 to 6% error on the test set. Okay, so that's just the function that we want to optimize. And now we can formalize that. Yes, please. Yeah, that's a good question. So here you have a reduction in the error, because essentially, if you see what's happening here is that you have two Gaussians. So the best separator would be just the vertical line. But since you have less samples, what the classifier learns is this boundary, which is a bit tilted. So if you add a red point here, well, the boundary will move will change toward the correct separator. So that's a case where you add noise, but it's even helping the classifier to perform better. Okay. So if you have much more red and blue samples, you will find the ideal separator. So that's why you have a decrease here. Okay. And so now we can formalize that. So the goal of the attacker is to maximize the generalization error on the unseen data with respect to the poisoning point. And this can be formalized in this way. So you want to maximize the loss function on some validation points. F is your trained classifier, and XC is the attack point. That's the main objective. I want to maximize the error on clean data. But this is subject to this constraint. And the constraint is that I have to retrain the classifier F star, including the attack point, XC. Okay? So you have two nested optimization problems. One is maximizing the error, and the other one is training the classifier. Because every time you change the training point, you have to update the model. That's why you have this dependency. And this is called bi-level optimization, because you have the outer problem and the inner problem is nested in this way. Okay? And this is a specific instance of this problem for the SVM. So if you use the inch loss for measuring the validation error, this is how it looks like. But this is just to show you that the dependency, so the only point where you see XC, which is the variable you are optimizing, is here, and it's here. So there is an implicit dependency of the outer function with respect to the inner problem. And the dependency is captured by the classification function. The classification function is the only thing here. F star is the only one that depends on XC. Okay? That was just to make this clear. And now, this looks very complicated, but there are ways, of course, you can use to solve that. And in particular, you can, again, compute the gradient of the loss function with respect to XC by using a trick. I'm not giving the details here, but for those of you who are interested, you can look at the paper. Okay, it's a paper from ICML 2012, and there are follow-ups. But in this case, the gradient is not very easy to compute, and you can understand why. So in this case, when you want to compute the gradient of the loss with respect to the attack point, you have to update the classifier. So this gradient has to keep into account that the classifier changes. Whereas in the evasion case, it was different. The classifier was fixed. Okay, we're not changing the decision function. And there is a trick, as I said. And the thing is that you can remove the inner optimization problem, so the training problem, with this equilibrium condition. So if you remove the learning problem with the KKT condition, the Karush-Kuhn-Tucker equilibrium conditions, you have now an optimization problem with constraints. It's a set of linear constraints. And then you can basically invert these constraints to find the dependency of the classifier parameters with respect to the attack point. I'm not giving the detail, as I said, but in this way, you can compute the gradient in closed form, and you can do that for many different classifiers. You can do that for the SVM, for ridge regression, lasso, and logistic classification, and so on and so forth. So all the classifiers that have clear optimization formulation and equilibrium conditions, for them you can compute this gradient. This is just how it looks like for the SVM. And as you can see, this more or less encompasses the KKT conditions in some form here. Okay, so that's the Asian of the problem. But if you're curious to see how to derive this, you can look at the paper. And this is what happens when you consider this gradient-based attack in the toy case we have discussed before. Again, this is the linear classifier. Now, what you can do is take a point from a class. In this case, I take a point, I clone a point from the blue class and flip its label. So I labeled it as red. That's XC at the first iteration, 0. And then you optimize it along the gradient direction. So you do this gradient ascent following this equation. And what happens is that in the end, you find a local maximum of the function. Okay? And this is very interesting because it also works for nonlinear classifiers. So this formulation is essentially equivalent for the linear and the nonlinear SVM using kernels. The trick is that this gradient allows you to go back and forth from the input space to the kernel space or to the representation space. So that's how it works, why it works for the nonlinear case as well. And now this is a simple example on, again, a toy digit problem. So we take, again, 2 digits. And in this case, the classifier aims to separate 4s from 0s, just 2 classes. What we do here is we take a digit from the 4, the class of 4, and we flip its label. So now you have a 4, which is labeled as 0 in the training set. If you just flip the label of this sample, the error goes from 0, almost 0, to, let's say, 1%. That's the iteration 0 here. Okay? That's just a label flip. So more or less, SVM is robust when you just flip the label of a few labels in the training set. So essentially, nothing interesting happens here. But then you optimize the point with the attack algorithm that I just discussed. And what you get is this kind of blurred image of a 4 that, I don't know if you can see it, but there's more or less the shape of a 0 in the background. And now if you add this image labeled as 0 into the training set of the classifier, you completely screw it up. And the error goes up, the testing error goes up to more than 20%, just by adding one image out of 100 training points. So the attacker is just controlling 1% of the training data. Okay? With 1% of control over the training data, in this case, you can essentially send the error from 0 to 20%. And in many applications, this is already enough to make the system inaccessible to legitimate users. So it's effectively a denial of service. And of course, you can iterate over multiple points. So if you add one point, then optimize another one in a greedy way, you can further increase the error. And here we go up to 35%, almost 40%, with less than 10% of poisoning points. Okay? I think I will make a break here. We can have a 10 minutes break, if it's okay with you. I can start again at 12:20. Okay? Okay, let's make a break then. Okay, so we've been discussing how to manipulate the training data to damage the classifier in the sense of maximizing the error. And in some cases, as you can see, the error can go up very quickly, I would say. I'm wondering if you are thinking to what may happen to deep nets. So are deep nets also okay. And so far it's not been studied very well. So it's not clear whether they are, maybe it's the cable. Let me see. So it's not clear if they are very, very vulnerable to this threat. And there is just one paper, which I think is very interesting, where they show that you can, so this paper is about interpretability of deep nets, so trying to understand when they make predictions, why they predict some sample in a given class. And they explain the predictions by finding the best prototypes that in the training set that explain this prediction. So it's like this image is classified as a dog because I know these 3 dogs from the training set. Okay, so that's what the paper does. And in, when they derive this prediction method, this explanation method, sorry, they also came up with a method to generate some adversarial training examples for deep nets. But they just present a simple case where they have the image of a dog labeled as a fish, so they flip the label. They add a bit of noise to this image, which is crafted as the attacker described. So what they do is they just use the KKT equations in the last layer, in the logistic classifier. For the logistic classifier, they compute the gradient in a very similar way to what I showed before. And then the gradient that you get, it can be backpropagated up to the input pixels. So you are essentially assuming that all the network layers are fixed and only the last one is changing. But anyway, doing this approximation, they were able to create some samples for the poisoning phase. Of course, when you retrain the network on the poisoning samples, all the other layers also change, right? It's not the only one, the last one that is the only one to change. They all change. But that's an approximation that they use to generate these samples. And what they show is that if you add this image of a dog slightly perturbed, you can flip the decision on these 5 test samples. So you can have the network believe that these are fishes, okay, instead of this nice dog. This is not a complete, availability attack, because you just, by modifying one training sample, you have 5 misclassifications in the test data, but that's at least a preliminary result that shows that you can also apply this attack to deep nets. The problem is that the computational complexity of this method to compute the gradient, as I discussed before, is quite high. And you have to retrain the classifier every time you need to update the gradient, to compute the gradient. And so we also developed a more, let's say, a smarter way to get an approximation of the gradient using an approach which is called back gradient or hyper gradient computation. And I'm not giving the details here because it's quite complex. But I just want to tell you that there is a whole area of research dedicated to the solution of these bi-level optimization problems, the same that we had for poisoning attacks. You have the same problem in meta-learning or learning-to-learn approaches. I don't know if you're familiar with that, but they're all characterized by bi-level optimization problems. But instead of maximizing the validation error, you minimize that. And you minimize that with respect to the hyperparameters of the classifier. And so there is a lot of new ideas to solve these problems in a much more efficient way. And here we just exploit one of them. Okay? But you can have a look to this part of the literature if you're interested in more efficient solutions for attacking deep nets in this case. And we're also doing that. So now coming to defenses. So how can we defend and protect the classifier against poisoning attacks? In this case, it's much easier than the evasion case, because by their nature, poisoning attacks have to be outlying with respect to the remaining training points. So if you inject a training point which is similar to the other ones, you will not change the decision function very much, right? So you have to inject things which are different from the rest of the training set. And for this, as you can see here, the red point is very far from the class of red points, and the same here. So these let us think that it's easier to detect these kind of attacks. But use this idea that they are outliers with respect to the training data. And therefore, there are 2 main approaches, again, that you can use to counter this attack. One is data sanitization, which essentially amounts to identifying the outliers in your training set and removing them. And the other one is based on the idea of robust learning, which means I have algorithms that are designed by knowing that there are some fraction of outliers in the training set. And they are designed to be robust against their presence natively. Okay? And now, just to give you an idea of one of these robust learning algorithms, this is one we proposed last year at the SMP conference. Well, the idea here, so this is applied to, in a case of robust regression. But the idea of this algorithm is basically, so the goal here is, let me just explain with an example. The goal here is just to fit this cloud of blue points. So the blue ones are the legitimate points. You ideally would like to fit a regression line to these points. The ones with these circles around them, they are outliers, just thrown at random in the data. Okay? So if you learn a standard regression, ridge regression algorithm here, you get this line, which is, of course, tilted with respect to the one that you would learn in the absence of noise, of outliers. What the algorithm does is that it computes the loss value for every training point, and it discards those for which the loss value remains very high. Okay, so you have to set a fraction of outliers in advance, and then you say those are the k points which have the highest loss with respect to my classifier, and I get rid of them. Then you fit again the classifier. So the red ones are the identified outliers in this case. At the beginning, you throw them at random. So you pick the red points at random, and you retrain the classifier. At this iteration, those red points are the ones which had the highest loss with respect to this line, and therefore those are ignored when you fit, again, the regression line, and so on and so forth. And at the end, when it more or less converges, you can see that it more or less identifies the majority of outliers correctly, and therefore it ignores them when fitting the line. So this is essentially the idea. It's called trim, and it's inspired, of course, by the robust statistics like TrimAdmin and this class of estimators. Yeah.
The ones that are not encircled.
No, I think it's the same number. So maybe it's a bit misleading because there might be some overlapping, but it's the same number. It's fixed. So you have to fix the number of, I think it's this n here. So that's the number of, you have to fix the fraction of outliers in your data.
The ones without the encircling.
So the circled ones are the outliers. If you have a circled red point, it means it was originally an outlier and the method correctly found it. Okay. Yeah, thanks for the question. And then, of course, we evaluated this method for an increasing fraction of poisoning points in the data compared to other existing robust regression approaches. And you see that ours is essentially identifying all the poisoning points. Now, this is not a full honest evaluation in the sense that the attack is ignoring the defense. Okay, so we are just optimizing the poisoning points as if we didn't have any defense. And so they are in some sense easy to spot. Okay, at least by a method carefully dedicated for that. Of course, this line, if you craft the poisoning attacks by accounting for the presence of the defense, what you would do is to inject more points, but they will be closer to the original points, just to be less outlying than the full attack, than the complete attack. And of course, this means that this curve will go up, but you have to inject much more points, much more stealthy attack points in this case. But you can fool it, okay? So a more honest evaluation will take into account this modified attack that also knows the defense. That's one of the points. Okay, now let's cover, if you don't have any question, we can cover some other examples of attacks against machine learning very quickly. There are some, so this is the overall view and taxonomy that we proposed in the survey paper, which is also associated to this lecture and tutorial. So you might want to have a look. And you can characterize them by intersecting the different attack goals that we defined with the capability of manipulating the data. And as you can see, so far we've seen integrity attacks obtained by manipulating the test data. That's the evasion setting. And availability attacks by manipulating the training data. That's the poisoning attack where you want to maximize the error, right? We're going to cover some other attacks here that aim to get some private or confidential information about the classifier by just manipulating the test data. So in this setting, we will see that you can query the algorithm with some well-crafted samples, and by observing the predictions, you can infer some private information about the classifier or the users. And then we will just see another example here when you manipulate the training set of the algorithm to allow specific intrusions during testing. So not to screw up completely the classifier, but just to allow some specific misclassifications. So regarding privacy attacks, this is an example by considering a face recognition system. And this was known as a hill climbing attack in biometrics, but it has recently been, let's say, rediscovered in this recent paper, 2015. So what they show is that if you can query the algorithm, you can then optimize your image by essentially trying to maximize the similarity with the given user. And so it's like computing a gradient in a numerical way. So you start from a noisy image, and you query the system, and then you try to maximize the probability of a given class, so a given user in this case. And at the end, you can, if you iteratively do this, you can eventually reconstruct the template image, so the face that you have in the training data. Okay, of course, you have some error, but more or less, the attacker has a lot of information. Okay, and this is obtained by starting from a random image. Okay, that's the true image of the user, and this is reconstructed from random noise by iteratively querying the system over and over. So that's an example of how you can get information about the training data by querying the algorithm.
So I got confused here. So the system, in which case, what is it?
It's a classifier that is aimed to classify different faces.
Okay.
So you may say, I want to be classified as you, for example. I start from a random image, and the classifier will give me the probability that this image is classified as you. Then you can perturb the pixels in random ways, right? It's a sort of black box attack. So you can perturb the pixels, and then you submit the new images to the system, and you see the one, which is the one that maximizes the probability of being classified as desired. And then you keep going, and in the end, you can find an image that has this very high probability value.
This assumes that, of course, the attacker doesn't have already the image of the person.
Yeah, it's not assumed that you can start from a random image. The only thing that the attacker can observe is the prediction probability.
So I guess the attacker knows that somebody has that specific label. So and he wants to get back to whatever is the image behind the in this case.
Sorry.
So I mean, I guess the attacker knows that a given system is able to attach labels to
Yes.
images of faces, and he may know that there is some guy. That
Yes, yes. You may know at least a name, let's say. Yeah.
So he knows the name of the person, but doesn't know the face. So
Yes, 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 yes. That's a kind of scenario, yeah. But the main idea, yeah. So this attack, I don't remember what they say in this paper, but the original idea that they found here in these very old papers was that there was some APIs available online that you can iteratively query. And so you can generate digital images, then the system will classify them, and then you can do this many times. And in the end, you can reconstruct some private information about the users. That's an example. Yes, please.
But in a real-world context, how likely is the possibility that the attacker has the access to the output probabilities of the model?
Yeah, maybe for faces it's a bit weird, but there are nowadays many systems which are served online as cloud services. So you have there is, for example, one which is Google Vision APIs. You can submit images, and it will return you the probabilities for each class of objects in these images. If you imagine this kind of setting, then you can do something like this. Of course, it makes sense if it's on private data. Otherwise, you reconstruct images. But it's anyway just an example to see that if you give your prediction probabilities out, one can learn something about your training data. So that's the point of this attack. The other example is exactly closer to what I was saying before. This is another very recent attack where you have a model which is provided as a service, maybe trained on some of your data, and then the user can just query the model to get the predictions back. So in this case, this attack is able to understand if a given image that the attacker has was part of the training data. Okay, so you can look at the probabilities, the distribution of probabilities that are predicted by the model, and based on that, you can say this was in the training set or not. So this is called membership inference attack. Okay, it's interesting to some extent, but you have to assume that the attacker has somehow access or knowledge of some of your training data, and he just wants to verify if this image was used to train your model or not. And there is also a countermeasure to that, so you can mitigate this problem. But this attack simply works because the distribution of probabilities for training point is very extreme. So you have a very high probability in the correct class, and all the rest is flattened more or less to zero. Whereas for samples which are not in the training data, you have more balanced distributions. So the classifier is not that secure on some given class. They're not so sure on the prediction. And I also think it just works with the cross-entropy loss and softmax, because this loss penalizes very heavily errors on the training set. So if you use loss functions which are, for example, less extreme on errors, less penalize the error, this attack is more difficult to perform. That was, again, just another example of an attack that may undermine the privacy of your system. And there is another one which is interesting. This time, this is a poisoning integrity. So I'd like to change the model or the training set in a way that I can misclassify some images in the test set during test. So assume that you have a classifier that discriminates between stop signs and speed limits, just two classes for simplicity. So what the attacker can do, if he has the model, is to add an additional class, which can be, for example, a stop sign with a sticker. And then you can use these samples to retrain your model, also to accomplish for this class. So the setting here is that you have a pre-trained model available online. Then the attacker takes this model, manipulates that, and again, releases it to the public. So if someone uses this model, which may contain a backdoor, then the model may behave as desired when the attacker activates the backdoor. And this means, for example, that if you have a car driving, using this backdoored model, when it sees a stop, so when it sees normal stop signs and speed limits, it works correctly. But when it sees the stop sign with the sticker, it recognizes that as a speed limit. So the sticker activates the backdoor in some sense. And that's another kind of attack. You see, this is a stop sign with a sticker, and it's recognized as a speed limit with high probability. Okay, is that clear? So it's again an example of poisoning, but very targeted to some specific points in the test set.
Sorry, just a question here. So
yes.
You're not showing that the discrimination boundary is changing. So it will be the same. But in fact, it will change, right?
Yeah, it will change. The point is that it will change in regions that will not affect the performance on the other classes.
Well, because in this case, it is a very simple classifier like a linear.
Yeah. If it's linear, it's a problem. First of all, you have just two classes, so you cannot add a new class. But in this way, this is exploiting, in fact, the high capacity of deep nets to fit data. So if you add a new class and it's reasonably far from the other samples in the representation space, then it's not really problematic for the remaining classes. That's why this attack is possible. Okay, make sense? Okay, then this part is moving towards the concluding remarks. So it's just a more relaxed part now, but the effort for understanding is reducing now. Okay, so it's a question that I like to pose also to the audience. So if all these techniques that create adversarial examples are really a security threat or not. Okay, so it's the fact that we have this image of pandas and we change some pixels to have a gibbon really a problem for learning algorithms, or is just a hype in the research field in some sense? So the first thing is one problem, and so the question is, we know that if we manipulate images in the digital domain, they can cause problems to learning algorithms. So there has been a line of research saying that effectively, if you craft the adversarial examples in the real world, they may not be as effective as they are in the digital domain. So the thing is, how would you just manipulate the school bus to be an ostrich, right, in the real world? It's a problem. So, and this has been questioned by many authors. And in the first work dealing with this problem, these authors, Kurakin and others, they showed that effectively, if you take your adversarial example in the digital domain, you print the image, and then you acquire again the image with the camera, the attack remains effective in some cases. Okay, so that's the very first experiment that you can, let's say, craft adversarial examples in the real world, at least in pictures. So the noise doesn't disappear when you print the image and you reacquire it. That's the main point. It's not a consistent experiment on millions of images. It's just on some tens of images. So we have to be careful in drawing conclusions here, but it's at least an example that it's possible. And again, we've seen that it's possible to construct eyeglass frames to mislead recognition systems, face recognition systems. And you can just print this frame on paper, and you can attach it to a pair of glasses, and it works. So again, in this case, the noise transfers also to the real world. Okay. So should we be really worried about this problem? So can this be a real problem in the real world? So that's the point. And then again, the research is not really agreeing on this point. So there were also some papers saying, no, they are not really a problem, because these adversarial examples only work if you acquire the image from the same perspective with respect to the original image. So if you have instead an object and you get farther from the camera, or you change the position, you change the pose, then these attacks are not effective. And they show effectively that in some cases, the adversarial examples were sensitive to scale. And so, for example, in the case of a stop sign, if you modify a stop sign, well, the car will be misled only at a given distance and position with respect to the sign, not at all scales. Okay, so that was the main point in this paper. But of course, some authors have demonstrated that you can also create attacks which are robust to these kind of changes, even if you change the pose, even if you change the distance. And this is the very first paper showing that. Let me see if I can show the video here. And that's a cat, manipulated image of a cat, which is recognized as a desktop computer. And as you can see, this is acquired from different pose and position and distance from the camera to the object. And so it's kind of robust to these kind of changes in the way you acquire the image. Okay? Of course, as you can see here, the noise is no longer imperceptible to us. And the way they craft this noise is very close to what we did when I was talking about the evasion attacks. The thing is that instead of just perturbing a single image, you perturb different transformations of this image. So you have the cat acquired from a given distance, then you change the distance, and you generate these different images of cats. You create the noise against all these images, and then you average the noise. And therefore, you have a kind of unique noise model that you can apply to all images, and that is robust to these changes in the location and pose of the object. And then the same authors have gone even farther. So they have created these 3D objects. So this is a 3D turtle, which is correctly classified. It's printed with a 3D printer, and it's classified correctly. That's the original model. Then what they did use this trick to have the turtle misclassified as a rifle. And you can see that the pattern is slightly changed in terms of colors and things, but this is consistently misclassified as a rifle. Okay. Now, a turtle misclassified as a rifle is not that scary, but a rifle misclassified as a turtle might be. And so this is again a way, to see that in the real world we can have problems with this in this case. And again, this is the case of the stop sign. In this case, they crafted this specific kind of noise, inspired by the fact that this is a paper from Berkeley. So in Berkeley, they noticed that you have a lot of traffic signs with stickers on top of them. So they wanted to create a noise resembling these stickers, which won't be suspicious to the policeman or to people just going around, right? So this is something more or less legitimate that you can find there. But if you apply these stickers, now a self-driving car may recognize this stop sign as a speed limit. So what I'm showing here is in the left image, you have the modified stop sign. So this will be recognized as a speed limit for most of the video duration. And you can see the prediction. It will appear down here. And this is the original stop sign, which is consistently correctly classified. Okay, so now I'm playing the video, and you can see that there's a difference. And this one is misclassified as a stop sign, as a speed limit, sorry. Let me play it again. And you can see that it's classified as speed limit in most cases, right? So from several distances and position of the traffic sign. In some cases, in just a couple of frames, it's correctly classified as a stop sign, but most of the time it's misleading the algorithm. And so now we can say that we can really fabricate objects in the physical world that can fool detection algorithms or deep learning algorithms or AI if you want. But of course, there's no large-scale experiment that thoroughly investigate these aspects. So these are just a couple of examples that were created. So we still need a large experimental investigation to draw some conclusions. But then there is a recent paper by Gilmer, Goodfellow, and others where they really discussed the realism of this security threat. And in particular, they focus on the problem of indistinguishable adversarial examples. So is it really important that adversarial examples remain indistinguishable to the human eye? So that was the main question. And the answer, in the end, that they draw in the paper is that this is not the case. So that in the end, it's not very important for the perturbation to remain indistinguishable. The only thing that is important is that they fool the learning algorithm. So that was the main conclusion. Of course, there are cases in which we need indistinguishability. For example, if you are at the border control and there is a face recognition mechanism which is supervised by the policeman, they can be instructed to ask people to remove glasses or these kind of things, especially if they have these fancy patterns, right, on them. So in some cases, it may be required for the adversarial examples to remain indistinguishable, but in most of the applications, it's not required. So that's the main point. And they explicitly say that they cannot find here. We are unable to find a compelling example that required indistinguishability of this example. So that was a main misconception which spread like around about 2013 up to a couple of years ago. But now I hope this will be clarified. So indistinguishability is not really the point in this case. And yeah, I think I can just wrap up now. And it is a recent field. So it exploded when this problem of adversarial examples was pointed out in this paper, intriguing properties of neural networks. But of course, I hope to have convinced you that we can go back at least up to 2004, where we can find people that were working on similar topics in the area of computer security, like in spam filters and these kind of things. And then I think now, more or less, we are managing to get the two areas of research more and more close together, okay? And if you're interested in knowing more, so this is the paper I was mentioning also before, where we describe all this historical evolution of attacks and what are the common points between the different things. So it's essentially a summary of this lecture, okay? And yeah, there is now, of course, this is, there are a couple of slides here to tell you that the problem is going outside of the technical experts. So it's now becoming of interest for a larger part of the society, different stakeholders of these methods. And so there are legal issues. If a self-driving car has an accident, who is responsible for that, for example? So there are all a set of problems which are now investigated. And there is a very nice paper, which is this one, The Black Box of AI, on Nature. So I suggest you to have a look at that. And then where the main point is also to require explainability and interpretable AI in some sense. So if a deep net is telling me that there is a cat in this image, I also would like to know why is there a cat. So I want to understand how what the system learned from the data, and if it learned something useful or not. And this is very interesting. Let me tell you this, because there is a case where you have for example, there was an error. So there is a famous paper where they show an error of a deep net. There's a ASCII depicted in the image, and it's misclassified as a WOF. Okay, so it's a simple mistake. But then if you look at the pixels that most affected the decision, you find that the network believed that the ASCII was a WOF because there was snow on the background. So the relevant pixels were just highlighting the snow in the background. So what happened in this case, it was that we had a bias in the training set. So the network was trained with WOF images, all displaying a WOF with a background of snow, with the snow background. So in the end, the network didn't learn the notion of WOF, but it learned the notion of snow. And so once you present any other object on the snow, it just tells this is a WOF. Okay, so that's a popular example. I didn't have the image here, but it's you can find it on the internet. So also explainability of these methods, it's a really important concern. And another thing is that, but to be honest, it's now very interesting because deep learning has become so popular nowadays. So before that, machine learning was not working that well. SVMs, decision trees, all these kind of previous approaches were not giving the performance that we observe nowadays with deep learning. And so showing that these algorithms were broken was not that interesting, not that interesting to the community. But now if you see that something has more or less superhuman performance, as they claim, at least on some tasks, and then you show that it fails very easily on these simple problems, then it becomes much more interesting. So that's why there is this huge focus nowadays. And now to conclude, we also have to say that humans can also be fooled in different ways. For example, and then you probably know this better than me because some of you are studying neuroscience, so I guess you know these things of hallucinations and illusions. And just to make a simple test, probably you know this problem, the bat and the ball problem. So if you read that, a bat and the ball together cost $1.10. The bat costs $1 more than the ball. How much does the ball cost? The immediate answer that one may give is that one costs $1 and the other costs 10 cents, right? But the exact solution is 0.5, so it's 5 cents. And this is due to the fact that if you reason in a very limited amount of time, you tend to simplify the problem and tend to give the first answer that comes to your mind. So even when humans are restricted in time to make their decisions, they may make wrong decisions as well. So this is not only a problem with algorithms, but also with humans. So that's the main point here. And I think if you know this book, this is very well explained there. This is the Nobel Prize in economics. Okay, I think more or less it's done. Of course, the main point of this talk is that we have machine learning algorithms that are empowering a lot of application nowadays. They are working very well, but this comes at a price, and then we have to take care also of the security aspects that this involves, right, in many different facets. Okay, that concludes the talk. Thank you very much for resisting up to the very last moment, and good luck with the remaining of the school. Thank you.